Hello everyone, my name is Mohammed.Islam and I am a postdoctoral at the University of Western Brittany in France. Today I would like to talk about EZIOTracer, unifying kernel and user space IO tracing for data-intensive applications. Here is the agenda of this talk. First of all, I will give an introduction and the state of the art. After that, I will describe the Linux IO stack before detailing the design of our tool EZIOTracer. Then, I will discuss the evaluation part of EZIOTracer considering several use cases. I will finish by concluding this talk and giving future work. Tracing is a popular method used for evaluating the performance of today's storage systems. Tracing consists in adding probes at strategic location of the program, and each time a probe is achieved, a handler is executed to record event in a log file, and then the execution of the program will be continued. The log file is analyzed online or offline to study the performance profile of the storage system. Although tracing is centered on low intrusiveness, but if we not pay attention to the number of the used probes and the amount of data to be recorded, the overhead could be considerable and the program execution may be disturbed. This slide presents the related work. Several tools are proposed to trace IO operations at the user space and at the kernel. The first category focuses on high-level metrics such as load contention and library IO buffer management, whereas the second category focuses on low-level metrics such as cache management and disk optimization tasks. But the problematic is that there is no tool designed to consider both levels in a unified way in order to fully understand, investigate, model, and optimize the complex IO behavior of modern applications. This slide presents the Linux IO stack. First, the user program makes a syscall, for example, read. The read syscall is redirected to the VFS, which represents an abstraction to support various file systems, such as block, in-memory, or pseudo-file systems. The kernel checks the page cache and serves the read request from the page cache if data exists. Otherwise, the read request is forwarded to the physical file system, which translates the read request onto a physical IO operation. The physical IO operation is passed to the block layer, where a block IO operation is created and scheduled according to various objectives, for example, to minimize hard disk head movement or to increase the overall throughput by merging small requests. Finally, the IO operation is served from the physical storage device. In this section, I will detail the design of EZIOTracer. At first, I give an overview. EZIOTracer is a unified IO tracer for both kernel and user spaces. EZIOTracer is composed of three components. The first one is EZIOTrace, an existing tool to trace IO operations at the user level for different IO libraries like pthread and OpenMP. The second component is EZIOTracer, a kernel tracer we developed to trace IO operations at various levels of the Linux IO stack leveraging eBPF, which is presented in the next slide. The third component is EZITrace Analyzer, ETA, an existing generic trace analysis framework. We modified this framework to merge both traces made by EZIOTracer and EZITrace in a unified trace. eBPF for Extended Barclay Packet Filter is a feature that was added to the Linux kernel since the version 3.15. The big advantage of eBPF is its capacity to run sandboxed programs such as monitoring tools in the Linux kernel without changing the kernel source code, while assuring high precision, low overhead, and system safety. This slide shows the detailed architecture of EZIOTracer. As aforementioned, EZIOTracer is composed of three main components. The first one is EZIOTrace, which is a user space tracer which traces calls from user process to popular HPC or data-intensive libraries such as OpenMP and POSIX thread. The second component is IOTracer, which is a kernel space tracer we developed to trace IO requests at each level of the Linux IO stack. The last component is EZIOTrace Analyzer, ETA, which is a generic analysis framework which retrieves the traces made by the two tracers and merges them into a single unified trace. This unified trace allows to get a global and comprehensive understanding of the application's performance profile. For example, the identification of the kernel level mechanisms slowing down user level requests, such as cache management and disk optimization tasks. Next, I will detail IOTracer, the kernel level tracer. As shown in the figure, IOTracer traces IO requests at various levels over the Linux IO storage stack, including the VFS, the page cache, the file system, and the block layer. In each of these levels, IOTracer uses different probes placed on kernel functions in order to mark the arrival of write IO operations or read IO operations. Each probe has an associated handler that is executed when the function in question is called. Each handler records in the trace a timestamp and a series of parameters that are specific to the function called. For example, the size and the address of the IO operation. In this slide, I will show how IOTracer records events. Using eBPF, the captured IO events are saved in a custom C structure, the struct log in the figure, which will be pushed to a circular buffer, the perf in the figure, using the perf submit function. Then data must be fetched in user space periodically with the perf pool function. In order to reduce the overhead of tracing, EZIOTracer allows enabling or disabling the use of IOTracer, the kernel tracer. To do this, the user can specify the use or not of IOTracer while launching EZIOTrace, which will send an activation command to IOTracer. A feature of IOTracer is its capacity to record IO events based on filters. This helps to increase the precision of the trace, to perceive the memory footprint, and to minimize the runtime overhead. IOTracer offers two different filtering methods. The first one is based on filtering by PID, and the second one is based on filtering by file or directory inode. For example, activating a filter by PID, this forces IOTracer to record only the event initialized by the process given by its PID. As aforementioned, EZIOTracer uses ETA, the generic analysis framework, to merge traces made by IOTracer and EZIOTrace in a unified trace. To do this, ETA first identifies the IO operation sequence that correspond to the same thread in both user space and kernel traces. For example, the thread number 1 in the figure. Then, based on the timestamp, ETA sorts and merges both IO operation sequences in a unified user kernel trace. In this slide, I will explain how the EZIOTracer components interact to make a trace. The managing component in EZIOTracer is EZITrace. So, first, the user launches EZITrace and specifies the filters to be used in IOTracer. Then, EZITrace starts recording the IO event of the application taking place in the user space, and it calls IOTracer while specifying the filters entered by the user to trace the IO operation in the kernel space. When the traced application ends its execution, EZITrace stops logging IO events and sends an end message to IOTracer. Finally, the ETA framework merges both traces in a unified trace. This slide presents a summary of the design of IOTracer. IOTracer involves several components. The first one is EZITrace to trace IO operations in the user space of different libraries like pthread and OpenMP. The second one is IOTracer to trace IO operations at various levels of the Linux IO stack, VFS, FS, page cache, and block, leveraging eBPF for low overhead, high precision, and safety. The last one is the ETA framework used to merge and unify the traces made by EZITrace and IOTracer. In this section, I will present the evaluation of our tracer, EZIOTracer. The evaluation has two goals. The first one is to demonstrate the ability of EZIOTracer to detect IO bottlenecks as well as to pinpoint the source of the performance problem. To do this, we rely on the theoretical slowdown caused by thread interference, SCI. SCI close to 0 means that the thread does not suffer from contention. Conversely, SCI close to 1 means that the thread spends all of its time waiting for IO due to contention. To compute the SCI score, first we identify the fastest thread IO operation, assuming that this IO operation does not suffer from contention. Then we compute the total slowdown caused by contention, which equals to the sum of the differences of the IO operation durations compared to the duration of the fastest IO operation. The thread SCI is the ratio of the total slowdown and the thread life duration. The second goal of the evaluation is to evaluate the time overhead of EZIOTracer comparing three software configurations. The first one is vanilla, in which the application is run without tracing. The second one is the EZITrace configuration, in which the application is run with the user space tracer only, EZITrace, in order to evaluate its overhead. The third configuration is EZIOTracer configuration, in which the application is run with the unified tracer EZIOTracer. For the evaluation, we use FIO as benchmark application with buffered and non-buffered IOs. For non-buffered IOs, the IO operation bypasses the page cache and access the storage device directly through the use of the ODirect open flag. For the experiment setup, we varied the number of used FIO threads from 1 to 64. In this experiment, we used a recent Linux version 5.10. First, I will discuss results for the first goal, which is the detection of I/O bottlenecks. We remember here, to do this, we compute the contention score SCI. For non-buffered I/Os in the figure, we show that both EZIOtrace and EZIOtracer have a small SCI score, which is less to 0.2, whatever the number of threads. This means that the variation of I/O times is low. To pinpoint the performance problem, we analyzed EZIOtracer truss in case of 32 threads. We found that all calls to write generate a syscall and generate event in VFS, FS, and block levels. This means that the performance problem comes from the kernel side, as all IOs are submitted to the block layer and there is no taking advantage from the page cache. Now, we pass to the case of buffered IOs. In the figure, we show that both EZIOtrace and EZIOtracer have a high SCI score. For example, it is more than 0.5 in case of 32 threads. This means that the variation of I/O times is high due to contention. To pinpoint the performance problem, we analyzed EZIOtracer trace in case of 32 threads. We found that user calls to write generate calls to VFS and FS, but zero block events. This means that the write traffic is mostly absorbed by the page cache. This means that the performance problem comes from the kernel side due to the variability of the RAM access times. Now we pass to the second goal of the evaluation, which concerns the overhead of EZIOtracer. Using non-buffered IOs in the figure in the left side, we show that the throughput increases linearly with the number of threads, achieving its maximum of about 330 megabytes per second. Also, we observe that both EZIOtrace and EZIOtracer have small overhead. For buffered IOs in the right figure, we observe that the throughput increases quickly and reaches its maximum of about 12 gigabytes per second with 16 threads. The instrumentation overhead of the user space tracer, EZIOtrace, is less to 5% in most cases, whereas the EZIOtracer, the kernel tracer overhead is about 26%. To summarize, in case of non-buffered IOs, we have small throughput, which means that we have a small number of events per second, and consequently, we have small overhead. Conversely, in case of buffered IOs, we have a high throughput, which means that we have a high number of events per second, and consequently, we have a high instrumentation overhead. To conclude, we have seen in this talk that tracing is a popular method for evaluating and investigating the performance of today's storage systems, and there are many tracers have been proposed for user space and kernel side, kernel Linux. But the problem is that there is no tracer considering both user and kernel spaces in a unified way. To fill this gap, we proposed EZIOTracer, which relies on EZIOTrace, an existing user-level tracer for HPC data-intensive applications. EZIOTracer, a kernel-level EZIOTracer we developed based on eBPF for low overhead, high precision, and safety. ETL, an existing generic trace analysis framework used to merge traces made by EZIOTracer and EZIOTrace in a unified trace. The evaluation part demonstrates the EZIOTracer ability to record the unified storage system user kernel performance behavior and shows that EZIOTracer has an overhead that ranges from 4% to 26% depending on the I/O intensity. For future work, we plan to test EZIOTracer with extensive experimentation using real HPC big data applications with different use cases. Also, we plan to extend EZIOTracer to support memory mapped I/Os, tracing, and other file system types like ZFS, and other storage interfaces like NVMe. Thank you for your attention.